Hello everyone, today's lecture I will be discussing about the introduction to analog communication. I'm Dr. Sandhya Patnaik, Assistant Professor EC Department, Narula Institute of Technology. I'll be covering up the topics of the basic block diagram of a communication system, the basic definitions of modulation, what is the need of modulation. The communication is a process of conveying message from the source to a destination. That is the definition that any layman knows. In, in the earlier days, the process of communication or transferring information was done by using some old some techniques like beating of drums, showing some symbols. For example, the white flag is a symbol of peace, or making the sounds of animals. So by these techniques, they used to convey information from one place to another. With the advent of technology, the process of communication has changed. The communication is now more efficient, and the, the technology has facilitated the long distance communication, and the quality of service of the communication system has increased. Some of the examples are like mobile communication, line telephony, radio broadcasting, and satellite communication. In telecommunication, the physical message, like sound, words, pictures, are converted into electrical signal, and this electrical signal is conveyed to a distant place where it is received and reconverted to the physical message through the receiver system. The electronic communications has undergone a chain of dramatic developments since the invention of by Morse in 1838. The invention of telegraphy took place in the year 1838. In 1845, the Kirchhoff circuits law was enunciated. In the year 1887, the invention of wireless telegraphy had taken place. In 1923, the invention of television. Thereafter, in 1936, the invention of FM radio. In 1937, the pulse code modulation was developed. In 1938, radar and microwave communication, followed by information theory and coding in the year 1945. 1948. In 1962, the satellite communication began with the Telstar 1, and a series of developments in the field of analog as well as digital communication, including the mobile communication and the development of the high-end modulation techniques, has changed the phase of communication systems today. The basic block diagram of any communication system includes the information source, input transducer, transmitter, and the signal goes through the channel where the noise is added. Then the signal is received by the receiver section, and then you have an output transducer. So each of the function of these blocks are as below. So what do you mean by information source? Information source here means the signal that has to be transmitted to the destination. That is, it can be in the form of voice, it can be in the form of video, sound, or data. So the information source is first converted to an electrical form by the help of an input transducer. So the input transducer is used to convert the information source which can be either sound, voice, or data to an electrical form. For example, in case of the radio broadcasting, a microphone converts the sound signal or the sound waves into the corresponding electrical signal. Now, the electrical signal which is generated at the output of the transducer section is applied to the transmitter section. So, in this transmitter section, the electrical signal is processed like some operations are performed like restriction of audio range, modulation, and amplification, and the signal is transmitted into the channel. Now, what is a channel? Channel is a medium over which the signal is transmitted to the receiver. The channels are classified into two types. It can be a guided channel, it can be an unguided channel. The guided channels are of different types like twisted pair, coaxial cable, optical fiber cable. And in the unguided medium, the different type of channels are like the terrestrial microwaves, satellite microwaves, and the broadband radio. The coaxial cable is an electrical cable which transmits radio frequency signals from one point to another point. And in case of optical fiber cables, the electrical signal is first converted to the optical form and then it is transmitted to the optical fiber by the principle of the total internal reflection. In case of the unguided or the wireless channels, the transmitting antenna radiates a modulated signal in the form of electromagnetic waves into the free space, and these waves radiate in all directions or in some specific directions, and the communication between the transmitting antenna and the receiving antenna takes place by different propagations like your ground wave propagation, sky wave propagation, space wave propagation techniques of the EM wave. The microwave RF microwave links are actually the point-to-point RF links between a transmitting antenna and the receiving antenna. Whereas in case of the satellite microwave communication, the transmitting earth station transmits the signal to the satellite placed in the orbit around the earth, like your geosynchronous orbit or your low earth orbit, and again the satellite communicates or reflects back the signal to the receiving earth station. The satellite communication frequency ranges are usually in the range of 11 gigahertz and 14 gigahertz, and it helps in the worldwide communication. Now, going back to the block diagram of the communication systems. Now, in the channel, the signal is affected by noise. Noise is usually additive in nature and it adds on to the signal that is being transmitted. So, noise is basically an unwanted electrical random signal which adds on to the original signal and causes a lower performance. That is, in case of a communication system, the signal power to the noise power, that is the signal to noise ratio, should be always high. The noise content in the signal should be less. Now this noisy signal is received at the receiver section where the signal is demodulated, amplified, and then given to the output transducer. So in this output transducer, the signal is converted back to the original format of the signal. That is, it can be your converted to voice, video, or sound, depending upon whatever is the input. So having discussed about having discussed about the different type of channels, noise, the receiver section, we now discuss about the classification of the communication system. So on the basis of the technique of the transmissions or the transmission techniques, we classify the communication system into two types. One is the baseband transmission system and other one is the carrier communication transmission system. So in the baseband transmission system, you transmit the electrical form of the baseband signal itself. So baseband is the original signal, that is your the sound or voice or video, whatever is converted into electrical signal, that is called as a baseband. So this signal, if it is transmitted into the channel directly, it is called as a baseband transmission system. Whereas in case of carrier communication system, what happens is the baseband is applied to a carrier signal where the process of modulation takes place and then you further transmit it. So in case of carrier communication system, you make a use of a very high frequency signal that helps you to transmit the signal over a longer distance, that is your carrier is applied and you apply modulation. The best example for a baseband transmission system is your short hole PCM systems between two exchanges. Here in this case, you do not apply any carrier and there is no shift in the range of frequencies of the signal. And these also can be applied over optical fiber communication, but this communication system cannot be applied or is not advantageous over a radio link. Whereas for a long distance communication, it requires modulation. So let me take an example to explain you the concept of modulation. Suppose if I tell you to throw a piece of paper, so what happens? So whenever you throw a piece of paper, it's just only a single normal paper. The paper will at max go a particular say a distance of a small distance x. Okay. But if I want this paper to go uh, to or to go to a longer distance, then what do we do usually? We put some solid object inside the paper, or we take a small piece of stone. We wrap the paper around the stone and we throw it. So what we observe is that the paper which is having the stone inside it. Okay, the stone is wrapped with paper. It travels over a longer distance. The same concept comes with your modulation also. So whenever you transmit the signal over using only the baseband, right? So baseband is the original signal that has to be transmitted from the source to destination. So if you transmit the baseband as it is more affected by noise because the power content of the baseband signal might be less. And when you apply a carrier signal, so what it does is, and it translates the baseband signal frequency. So baseband signals are usually the audio signals or the video signals which are at a lower frequency. So when you apply a carrier signal, you translate the overall frequency of the signal, modulated signal, to a higher frequency range. And the higher frequencies are more immune to noise, and these travel over a longer distance. So the modulation is a process where a few parameters of the carrier, like say amplitude, frequency, or phase, are changed with respect to the baseband signal. So to sum up everything, let me define. So baseband signal is the original signal that has to be transmitted, and carrier signal is the signal that helps you to carry the information signal. So here the carrier signal is modulated by the information signal. So usually this carrier signal is for higher frequency, very high frequency, uh, than the baseband signal. So the modulation overall is explained as a process where the few parameters of the carrier signal like amplitude, frequency, or phase is changed with respect to the instantaneous value of the baseband signal or the modulating signal. Discussing about what happens to the signal when you perform modulation. Let us consider a baseband signal MT given by AM cos omega MT, a carrier signal CT, it is given by AC cos omega CT. So the baseband signal and the carrier signal are applied to the balanced modulator. The output of the balanced modulator is given as your AM into AC cos omega MT multiplied with your cos omega CT. This over here is a DSB AC signal. So if we expand this, what we get is your AM into AC by 2 cos of omega C plus omega MT plus cos of omega C minus omega MT. So what we observe is that in the modulator signal, the the modulated waveform is having two frequency components. One is your omega C plus omega MT and other one is your omega C minus omega MT. So cos of omega C plus omega MT is your upper sideband and cos of omega C minus omega MT is your lower sideband. So this ST is your modulated waveform. So initially we had taken a baseband signal which is your having frequency cos of omega MT. Now when you apply a higher carrier signal whose frequency is very high, it's centered about omega C, it is getting translated to a high frequency and the frequency components are omega C plus omega MT and omega C minus omega MT. So this is called as your frequency translation. The baseband signal, which is of lower frequency, is now translated to a higher frequency by the process of modulation. Consideration the frequency translation and explaining the need for modulation. So suppose you are transmitting a few baseband signals through a single channel. This is the same channel. So the baseband signals might be having the frequency nearby. So they will be starting to interfere with each other. But instead of transmitting the basebands together through the same channel, if you perform modulation, then what happens is the signals are translated to a higher frequency, which is centered about the carrier frequencies. And if you transmit these signals to the same channel, but because of multiplexing, they will not interfere with each other. Next advantage of frequency translation is your practicability of the dimension of the antenna. So the minimum height of antenna for transmitting an effective for particular frequency is equal to the 1/4 of the wavelength of the signal which you are transmitting. So if you want to transmit an audio signal or a baseband signal of 5 kHz without modulation, then the dimension of the antenna will be equal to lambda by 4, that is equal to C by 4f. So lambda is equal to C by f, where C is the speed of light, that is equal to 3 into 10 per 8 meter per second, and f is the frequency, that is a 5 into 10 to the power 3 kilohertz in this example. So for this particular frequency of the audio signal, what will be the dimension of the antenna? So if you solve this, we get it as equal to 15,000 meter, that is nearly equal to 15 kilometers. So it is not practical to design antennas of this huge dimension. So instead of that, if you perform modulation and then you transmit the waveform, so you're applying a carrier signal to the audio signal and then you perform modulation and you transmit, the dimension of the antenna will be less. So when you perform modulation, the frequency translation takes place, that is the up conversion of the frequencies from a low frequency to the high frequency will take place. That is, the carrier signal, say you are applying, is equal to 10 megahertz to the audio signal of 5 kilohertz. So the modulated waveform that is generated out of this is nearly centered about the carrier frequency, that is equal to 10 megahertz, nearly equal to 10 megahertz. So what is the dimension of the antenna for transmitting a 10 megahertz signal? That is, the modulated waveform is now 10 megahertz. So lambda by 4 will be equal to C by 4 into 4 by f, that is equal to 3 into 10 power 8 divided by 4 into 10 power 7, that is nearly equal to 7.5 meters. So what we observe is that for a unmodulated signal, that is, you are transmitting the baseband signal as it is, then the dimension of the antenna is equal to nearly 15 kilometers. Whereas if you perform modulation and you transmit the modulated waveform, the dimension of the antenna is reducing to 7.5 meter. So it helps to reduce the antenna dimension practically. Next problem that will be solved by applying modulation is your narrow banding. You can perform narrow banding. Suppose if I say there is a radio station which is wants to transmit a frequency of from range from 50 hertz to 10 kilohertz. So what is the ratio of the highest to lowest frequency over here? That is nearly equal to 200. So the dimension of the antenna to transmit a 550 hertz signal and to transmit a 10 kilohertz signal is totally different. So this band edge ratio is nearly equal to 1 is to 200. So this is practically not possible. So you have to design an antenna for 50 hertz, and that will be too long for a 10 kilohertz signal. So what is the best solution? When you have a wide range of signals to transmit, then what you do is these baseband signals can be up-converted by performing modulations. That is, you apply a carrier signal of say 1 megahertz, where you translate the signal to frequency centered about 1 megahertz. So whatever is a baseband signal, you apply a carrier signal in such a manner that it is you're able to transmit, you're able to get into a single transmit to a frequency centered about the carrier frequency. So by performing modulation, you are able to perform narrow banding.